How do you take a tiny little blueprint and scale it up into a massive skyscraper? Or how do video game designers create these huge, realistic 3D worlds? Well, the secret, more often than not, comes down to triangles. Today, we're going to unlock two of the most powerful shortcuts in geometry for proving triangles are similar: SSS and SAS.
So, let's kick things off with a puzzle. How do you prove that two triangles have the exact same shape, but they're just different sizes? I mean, the traditional way, it feels like a total chore. You'd have to measure all three angles and all three sides. That's 6 different things to check. It's a lot of work.
But what if I told you there's a much better way? A shortcut. What if you could prove the whole thing with just a fraction of that info? Well, guess what? You can.
And that's exactly where similarity theorems come in. You should really think of them as power-ups for your geometry toolkit. They save you time, they save you a ton of effort, and they give you that absolute mathematical certainty you need.
Okay, our first tool is the side-side-side similarity theorem, or SSS for short. And yeah, as you probably guessed from the name, this one is all about the sides.
The theorem itself is actually beautiful in its simplicity. It just says that if you can show that the ratios of all 3 pairs of corresponding sides are equal, then bam, the triangles are guaranteed to be similar. You don't even have to know a single thing about the angles.
So, how does this actually work in practice? Let's put it to the test. We've got one big triangle here and 2 smaller ones. Our mission is to use this SSS shortcut to figure out which of the little triangles is a perfect, tiny clone of the big one. You know, the easiest way to do this without getting all mixed up is to just be systematic about it. We're going to compare the shortest sides with the shortest, the longest with the longest, and then the ones left in the middle. If all those ratios turn out to be the same, we've got a match. All right, first up, let's look at triangle ABC versus triangle DEF. The shortest sides give us a ratio of 8:6. The longest sides are 16:12, and the middle ones are 12:9. Now check this out. Every single one of those fractions simplifies down to 4/3. The ratios are identical. Boom. We've just proven these triangles are similar.
Okay, now for the other comparison with triangle GHJ. The shortest sides, ratio of 1. The longest sides, also a ratio of 1. But wait, look at the last pair of sides. 12/10 simplifies to 6/5. Since that last ratio doesn't match the others, nope, these two triangles are not similar. It's really that clear-cut.
But here's where SSS gets really powerful. It's not just for checking if triangles are similar. You can actually use it to make them similar by solving for missing information.
Take this problem, for instance. We're asked to find the value of x that will force these two triangles to be similar. So what that means is we can just assume the sides are already proportional and use that fact to build an equation and find our unknown. So we start by setting up a proportion with the corresponding sides. We'll set the ratio of 4:12 equal to the ratio of x minus 1:18. And from there, it's just a little bit of algebra. We cross-multiply, we simplify the equation, and then we work to get x all by itself.
And just like that, we find out that x has to be 7. And if you were to plug 7 back into that expression for the side length, you'd find that all the side ratios match up perfectly, confirming our triangles are in fact similar.
All right, SSS is officially in the toolkit. Now let's grab our next shortcut, the side-angle-side similarity theorem, or SAS. And as you can probably guess, this one involves a mix of sides and one really crucial angle.
Now, what's really important here is the fine print. For SAS to work, 2 conditions have to be met. First, you need one pair of angles that are exactly the same, congruent. Second, the sides that form that angle must be proportional. That angle has to be the one that's included or kind of sandwiched right between the 2 sides you're comparing. Now, this might seem kind of abstract, but SS similarity is incredibly useful. It shows up all the time in construction, engineering, design. Really, anytime you need to make sure different sized pieces keep the exact same shape.
Let's say, for example, you're building this lean-to shelter. For it to be stable and, look right, you need the triangular support on the right end to be similar to the one on the left. So can we use SAS to confirm this is even possible with these measurements? Well, let's check our 2 conditions. First, the angles. The included angle on both triangles is 53 degrees. So, check, they're congruent. Second, are the sides that form those angles proportional? Let's see. The ratio of the shorter sides is 9/6, which is 3/2. The ratio of the longer sides is 15/10, which is also 3/2. So, check.
Both conditions are met, so SAS gives us the green light. Yep, you can totally build that second support, and you can be confident it's going to be a perfect, scaled-up version of the first one.
So let's wrap this all up. It's time to officially add SSS and SAS to your ever-expanding geometry toolkit.
Here they are, the big three shortcuts. Along with another theorem called angle-angle, or AA, the SSS and SAS tools we just covered are your absolute go-to methods for proving triangle similarity quickly and efficiently.
And that, right there, is the big takeaway. Why on earth would you measure all 6 parts of a triangle when you can prove the exact same thing with just 2 or 3? These theorems are all about working smarter, not harder.
And that brings us to a final thought. Now that you know these shortcuts, you're going to start seeing them everywhere. Seriously, from the way shadows are cast on the ground to how artists create the illusion of perspective in a painting. So the real question is, where else in the world around you are these similarity rules secretly at work?